The key to getting a higher success rate, and therefore a better utilization of the medium, is to have carrier sense. That is, nodes should be able to tell when another node is already communicating on the medium and not start a communication itself. And when we have multiple nodes doing this with carrier sense, it can be called CSMA, carrier sense multiple access. In this case, it seems clear that the red node can detect that the blue node is talking because the blue node started earlier. What about if they start talking at the same time? You might hope that they both notice and both recover from that kind of collision, but there's a catch where there's a delay between the time that one node starts sending and another node is able to sense it, even if they start at the same time. We've been drawing blue's communication as a straight line from when it starts to when it ends, but the picture in reality is more like this, where from blue's perspective, it started at one point and ended at another point, but it takes a while for that signal to travel to other nodes throughout the medium, and so it's actually much later, perhaps, on the scale of the communication speed, that some other node discovers that blue started. And so if blue and red both start at the same time, they both think things are okay for a while, and at least in this picture, red is almost halfway through its message before it discovers that B was talking, and blue at the same time also discover. So we need ways to do better than this picture, because if they both discover there's a collision and then just randomly wait, we're pretty much back at slotted aloha. At a minimum, we need to do the same thing we were doing for slotted aloha, which is blue should not keep trying to send a longer message after it's discovered a collision at the A level here between red and blue. So it can stop early at that point, but also red and blue can stop much earlier. They can stop at the point where they discover that a conflict is detected. So the picture should look a little bit more like this. As soon as the blue and red regions overlap, then that means each of blue and red are discovering that there's a conflict and they stop sending a signal at that point. And that means they'll be able to try again much faster than if they didn't both stop. There has to be some overlap here for red and blue to detect each other. And so that's going to be a concern, but it's less of an issue than the distance between the red and the blue node and how long that signal takes to get there. For retries, we can do the random delay before retry, and that's a good starting point, in which case we might have a picture that looks like this, where red and blue both detect the problem, and then red starts and then blue starts. But the way we improve over slotted aloha is we don't need slots after all, and we do better than unslotted aloha because we're doing things at a finer granularity. Instead of sending a whole chunk and then checking whether there was a collision during that chunk, because we can detect early that two nodes are talking at the same time, they can stop earlier, they can restart earlier, and they don't need to be aligned on slot boundaries. Another way that we improve over slotted aloha is exponential backoff. Instead of flipping a coin and with p probability trying a resend on the next slot, we use an exponential backoff strategy similar to TCP, where a node will wait a certain amount of time, a little bit random, and then it'll wait a random value about twice as long, and so on. This tends to space out the communication and adapt and create fewer conflicts. If you work through this, it turns out that the overall efficiency formula looks like this. We would hope for 100%, but it's going to be limited by the maximum delay for a signal, that is how soon red can tell if blue started communicating. And it's also going to depend on the maximum duration that blue talks when it does get started. So if blue talks for a long time and everyone else can see that, if it's long enough, they will all just have to wait. So the longer we make this, the more efficient it is for blue, but the less we are able to swap among different communicating nodes, and so that can increase latencies at the expense of throughput. So ideally, the time to propagate to all the other nodes is very small, and you make the transmission as big as possible, because that will make the denominator of the nested fraction larger, which makes the overall fraction smaller, which is in the denominator of the efficiency fraction. And so we want that to be small, as close as we can get to 0 to get towards 100% efficiency. For example, if you allow a node to communicate for 5 times as long as it takes for the signal to cross all the other nodes, then this is a 1 here and you get to 50% efficiency already. Turn up the dtrans a little more and you can get above 50%.